This video I'm going to compare my WaveRunner 64Xi against my original LeCroy 7200. The 7200 is a modular scope. In this case I have a 7242A and a 7262. See, it has GPIB on the back, printer port, and a RS-232 port. I like the heatsink here. You can kind of see all the fans in it. Consumes quite a bit of power. The 7200 was released in 1989. The 64Xi was released in 2006. The weight of the 7200 is roughly 60 pounds the way it sits, compared to about 15.5 pounds. 7200 is 17 by 9.5 by 24 inches, where the 64Xi is 10.25 by 13.4 by 6 inches. The display on the 7200 is 7.5 inch. It's an amber, where the 64Xi is a 10.4 inch color touchscreen. The cost of the 7200 when it was released would have been roughly $33,000 to $45,000. In today's prices that would be roughly $62,000 to $85,000. The 64Xi when it was purchased was $11,500. With the extra software, it adds an additional $8,060. So roughly in today's prices about $20,000 compared to about $63,000 or so for the 7200. The bandwidth of the 7200 in 50 ohm mode is 500 megahertz compared to 600 megahertz on the 64Xi. The 7262A, the high-speed plug-in, is actually 4 gigahertz at 50 ohms. The 7242, when using a 1 meg input, is rated for 250 megahertz. 7242 will sample at 1 gigasamples per second in dual channel mode. In interlaced mode it will run at 2 gigasamples. Compare this with the 64Xi, which will do 5 gigasamples per channel and 10 gigasamples interlaced. To run interlaced mode with the 7200 requires an external unit. It's this thing here. This is essentially a delay line. This is a homemade one. This actually delays the signal 500 picoseconds and basically performs the interlacing that way. With the unit that was sold with the scope, there's some dip switches. These set the delay line. Obviously with the 64Xi, you just throw a switch. This is all done automatically. In repetitive mode, the 7242 will do 20 gigasamples per second, and the 7262 will do 100 gigasamples per second. Wrist mode on the 64Xi is 200 gigasamples per second. The memory depth on the 7242 is 50K points per channel. They were available up to 1 meg. I actually have some of those units for my 7200A. The 7262 has 20K per channel. Compare that with the 64Xi, which will do 2 megapoints per channel. Vertical resolution on the 7242 is 8 bits. It'll run enhanced mode up to 11 bits, but that caps the bandwidth to 8 megahertz. The 7262A will run 10 bits. The 64Xi, on the other hand, will run 8 bits as well, and 11 bits enhanced. I'm not sure about the hardware design of the 64Xi, but I do know a 7242 contains 8 A to Ds, 4 A to Ds per channel. So when you're running interlace mode, all 8 A to D converters are running. For the software for the 7200, everything was included in the base price. For the 64Xi, everything that you want to add is an additional cost. There's 2 catalogs here, one from 2007 and the other one from 1990. This is how I found the cost for the 7200. You can see in the back of the catalog there's a sample capital equipment justification, and we show here the cost of ownership. And you can see here the scope was originally priced with the 7242 at $33,000. And again, this scope is actually having 2 plugins, and the plugins are a little newer. There's the original asset tag from the United States Air Force. You can see where the 7200 uses a floppy, 3.5-inch floppy drive. Obviously the 64Xi is new enough, there are no floppies. It does use USB, so you can plug your flash drive into it, a little bit more convenient. You can see the 7262, these are all SMA connectors, and BNC for the 7242. On the 64Xi, everything is a BNC type. See how the plugins come out. Made in the USA. Quite a bit of heft to these. You don't see many of these high-speed digitizers. I have 2 of these for the 7200A that are newer style than this. All 3 of the digitizers, these all came from an employee of LeCroy. He managed to pick these up in an employee sale. Had them sitting in his garage for quite a few years. And when I found out he had them, I just bought all of his parts from him. Just looking inside the 7200. See the 2 plugins. Down here is the power supply. It's the video board, CPU board. It's a 68000 processor. Power supply here. This is an MFM hard drive here. This cable runs up to the keypad. CRT. See the floppy drive down inside. Scope's actually quite clean. Small mod here. It's actually a battery pack that I use. It charges when the scope's in use. It's used to keep the VRAM refreshed. But I've owned the scope now for quite a few years, and it's actually been quite reliable. I've also had the 64Xi apart a few times to do repair work on it when I first received it. I won't be taking that apart today. A few things I noticed with the 64Xi. These knobs are just a press fit. and when I was carrying this system, the knobs actually fell off while I was walking around with it. On this unit here, you can see there's actually an end cap on these. This pops off and there's a screw down inside of these. Here, if you can, that prevents this thing from coming off, so that's not a press fit. I've saved some of these knobs from different units that I've had to repair. You'll see these things get shipped on eBay and the shafts will be broken off and stuff, so I've been pretty fortunate. I was able to call over to Germany to get some of the replacement parts for this unit. So everything on it functions. These are pictures of the WaveRunner when I had it apart to install the new solid state hard drive and the added memory. So I've moved the two scopes into my office. To start, so I want to do is show the boot up times for the two units. Keeping in mind that these two scopes are basically 27 years difference between the two of them. I'd mentioned that I'd had the 64Xi apart. This particular unit came with 256 mega RAM. This unit now has 1 gig of RAM in it. The original hard drive has been replaced with a SSD. So far that's worked out quite well. The scope boots very fast, and the added memory, I found that it's made the scope very responsive. Originally, when I tried using the scope, it would actually hiccup depending on what I was trying to do with it. That doesn't seem to be the case anymore. I've actually, I tend to like the scope now that I've had it for a while, and made those couple of changes to it. So what I've done is I've hooked up 2 of the channels for each scope. We've got a 10 megahertz oscillator feeding to them. And I'm just going to turn them both on. Both scopes have been configured the same way. Just see how long it takes for both of them to come up. I'll take the time to mention that the 7200, while it does use an MFM drive, they limited the number of drives that they actually allowed you to use in it. I picked up a few used ones. One of them was a Seagate drive, which I've had very good luck with in the past. I connected the original hard drive and the Seagate drive to a logic analyzer, and then looked at the data bus to see what the difference was, and then made a modification to the Seagate drive to get it to run in the 7200. It's proven to be a very reliable system this way. So we can see the 7200's up, waveforms are being displayed. Keep in mind that solid state drive, adding that to the WaveRunner, this WaveRunner boots quite a bit faster than what it used to. And there you have it. So the 7200 wins this battle. Hopefully you're actually spending your time actually using the scope and not just booting it up. I'm going to go ahead and terminate the input. Both scopes are set to auto trigger. Both set to single grid. Let's just show channel 1. So just looking at the noise floor here, all I'm going to do is crank this up here a little bit. 7200 is set to 5 millivolts per division, where the 64Xi is set to 2 millivolts per division. Fairly similar. We're going to go ahead and apply our signal again. Okay, and here we're looking at 10 nanoseconds per division for each scope. Again, this is with a 10 megahertz signal. See all the display up here for the 64Xi. You can see it making the measurements here. We can do the same. Just do display, hit basic. What I'm going to do now is just increase the frequency. Same waveform, this is 100 megahertz now. Both scopes have been set to 50 ohm input. Here we can see we're reading about 320 millivolts peak to peak on the 7200 and roughly 350-ish peak to peak on the 64Xi. This is now 2 nanoseconds per division on both scopes. You really see the sample rate starting to hurt us here quite a bit. You can see the dots in this now. This is the difference of 1 gigasample per second versus a 5 gigasample per second. This is looking at 200 megahertz now. See, the 7200 is really starting to break up pretty bad. Peak to peak on this is like 270. Peak to peak on this is about 280, 290. This is with a 400 megahertz signal. You can see now the 7200 is really broken up pretty bad. If I go ahead and select interleaved, you see this will really clean this thing up quite a bit. So with a 500 megahertz signal, so you can see here, even with interleaved, the 7200 can't pick this up. You can see I've gone ahead and installed the delay line. It's now running in 2 gigasamples per second, non-interleaved. Both scopes set at 1 nanosecond per division. And you can still see the 7200 with that lowest sample rate. It's having a pretty rough time with this. Of course, the big advantage with the 7200 is I do have the other plug-in available. And again, this second plug-in is rated for 4 gigahertz analog bandwidth. Okay, here we are with the high-speed digitizer set to 1 nanosecond per division. This is also at 200 millivolts per division on both, so the same scale. So now let's go ahead and zoom in here a little bit. Here we're looking at 200 picosecond per division. This is with a 550 megahertz clock now. As you can see here, I'm just running these cables into a couple of BNCTs. One end isn't even terminated. That's a pretty shoddy setup at best. But it gives you an idea how well this second digitizer will do if you're working with repetitive signals. I've gone ahead and replaced our BNCT with a normal splitter. Both scopes are set at 50 millivolts per division, both running RIS. This is with a 600 megahertz signal applied. 7200's got a nice feature. You can just hit a button here to get the averaging right from the front panel. It's a 900 megahertz waveform now. So peak to peak on the 64Xi right now is reading 90.75, 90.8. 7200 currently is reading about 104 millivolts. So this guy, even though it's only rated for 600 megahertz, is reading very similar to what the 7200 is. And this is currently with a 900 megahertz signal. So it's pretty impressive. Okay, we can see now we're putting out a 1 gigahertz signal. The 64Xi is reading roughly 78 millivolts peak to peak. And the 7200 is reading roughly 96 millivolts peak to peak. So she's starting to get attenuated pretty bad now for the 64Xi. Still doing a pretty decent job though. Okay, we're now at double the frequency of what the scope was rated for. It's a 1.2 gigahertz signal. We're now reading roughly 85 millivolts peak to peak versus 55 on the 64Xi. Sure, a few of you have probably seen this kit. This is an evaluation kit that Tektronix put out for their oscilloscopes. It basically allowed you to do some benchmarking between their scopes and their competitors. It was a very simple board, and this book walks you through basically some different tests. There's probably 5-6 different tests that you could run to try to see if your scope would be able to handle the waveforms that they would throw at it. My plan for testing the scopes is to use an ARB. I have a Tektronix Sony ARB. It's an AWG 2041. This particular ARB has a mega memory, and it can output at 1 gigabit per second. So it's fairly flexible. So this is a LabVIEW program that I've written to exercise the ARB. It's just a generic program. I've got some other ones I use when I run some automatic tests. This is a terminal program called RealTerm. It's currently set for 9600 baud. It's displaying the data in hex. If we select serial data stream with our program, and we'll program in the ARB, see our pattern here. We're spitting out a AA550108, and it just repeats. So I'm able to change this pattern to whatever I want, whatever baud I want. One of the nice things with the ARB, this particular scope has a serial decoding option. They can do I2C, SPI, standard UART, CAN. So there's a slew of different protocols. It's very flexible. So I'm going to give some demonstrations of that as well. So what I've done here is I've entered 0 through F in our serial port. So when we output our serial stream, we should now get this data instead. You can see here the stream is quite a bit longer now. As you can see, it's counting up now, 0, 1, 2, 3, up to F, and then repeats. That concludes part 1. In part 2, we'll further evaluate the oscilloscopes using the ARB.